We're going to be looking at solving our polynomial functions, and as we said, there's not a direct way to do this like there is with quadratics where we have the quadratic formula. You just have to use several different tools to help you eliminate some possibilities and to come up with your solutions. One of the tools that we use is the rational root theorem, which says that if there are any rational zeros, they will be a factor of the constant term divided by a factor of the leading coefficient. That helps us narrow down our rational roots. We'll use things like Descartes' rule of signs, where we use the Descartes' rule of signs to determine how many positive real zeros that we have or how many negative real zeros that we have. Now these get into our real numbers. It still doesn't tell us about our complex numbers, but these are tools that we use to help us as we go about solving our polynomial. So let's look at some. There's not any direct way to solve them. You're going to have to deal with, okay, we will try this. If it works, that's wonderful. If it doesn't, then we have some other possibilities to try. We'll also use some things like the intermediate value theorem that we talked about in a different lesson, and how that can help us narrow down some possibilities. And here's our polynomial. Now, we could always check for factoring, but we can't factor this one by grouping, so we want to be able to solve it. So let's use some of our tools to help narrow down. If we used our rational root theorem, the factors of 10 are 1, 2, 5, and 10. And we would have the positive and the negative. The factors of 1 are 1. So if there is a rational answer, it will be one of these 8 numbers. So we've just gone from infinity down to 8. Well, that's helpful. If we use Descartes' rule of signs, notice here we have no sign changes. So that means we're going to have 0 positive real roots, which means that we can now do away with the positive choices. And it looks like that's going to do away with the whole choice. But that means now that all that we can possibly have is -1, -2, -5, and -10. Because from Descartes' rule of signs, we know that there are no positive real roots. So there's definitely no positive rational roots. If we want to find out about our negative roots, well, we can plug in -x. And again, the ones that are going to change are the terms that are to an odd power. So that's going to be -x cubed plus 12x squared minus 21x plus 10. So we change from a negative to a positive to a negative, and a negative to a positive. So we have either 3 or 1 negative real roots. Now, we know we have at least 1. So when we start, we're going to start with our negative numbers, and we've already put those there. So we've got 1, 12, 21, 10. And I'm going to start with -1. Most likely your answers will be close to your origin. So we bring down, we get -1 plus 12 is 11, -11 plus 21 is 10, -10 plus 10 is 0. So -1 was a root. What we have left then is a quadratic, x squared plus 11x plus 10. Setting that equal to 0, well, we can actually factor this one, x plus 10, x plus 1. So we get x plus 10 equals 0, or x equals -10. X plus 1 equals 0, so x equals -1. And then we found from our synthetic division that x equaled -1. So now we have our 3 roots. Well, that one turned out fairly nice, and it was easy to find that first root. So let's look at a second problem. And sometimes your problems do turn out, you just happen to pick that first one, that right one the first time. Sometimes you have to do a little bit more work. So we have 2x to the fourth plus 3x cubed minus 11x squared minus 9x plus 5 equals 0. Okay, now in this one we're going to have 4 roots. So that's a good bit more. As far as our this is plus 15. As far as our possibilities go, we have the factors of 15, 1, 3, 5, and 15 over all of our factors of 2. So that's over 1. And it's over 2. So we'd have plus or minus 1/2, plus or minus 3/2, plus or minus 5/2, plus or minus 15/2. So that gives us 16 different possibilities. Well, let's see if our rule of signs will help us. We have positive, positive, negative, so we have one change of sign. We have 2. So we're going to have either 2 or 0 positive real roots. If we substitute in negative x, okay, we're going to have 2x to the fourth. That's going to be a negative x cubed times negative 3 is a positive 3x minus 11x squared plus 9x plus 15. And again, if you look at the original, the ones whose signs changed, well, this was supposed to be a plus, so it was a good thing I checked here. The one whose signs changed were the ones that were raised to an odd power. So that should be a negative. It was I wrote down the wrong sign. So our squared, it stayed the same. Our 9x changed. So now we have 1, 2. So we have 2 or 0 negative real roots. So we're not even guaranteed that we have a real root. But if we do have one positive one, then we know we have a second one. So we're going to go through and try to find these. Okay, let's use synthetic division. Now again, the only thing you ever used this equation for was to find those negative roots. Always go back to your original. So we have 2, 3, negative 11, negative 9, 15. And I'm going to start with positive 1. So 2 times 1 is 2, plus 3 is 5. 2 times 5 is 5, minus 11 is negative 6. 2 times negative 6 is negative 6, minus 9 is negative 15. 1 times negative 15 is negative 15, plus 15 is 0. So that was very nice. It starts out, so we know that x equals 1 is a root. Now what we have here is what we call a reduced equation. This was 2x to the fourth. So in my answer, this is 2x cubed plus 5x squared minus 6x minus 15. So I have a reduced equation, and I'm going to go through then and try to find my roots of it. I don't have to use my original one anymore because I reduced it down, and so this is the other factor. I found one factor, x minus 1. This was my other factor. So I'm going to start. Now I always check, this ended in 15. And this was 2, so it's still all of those same factors. Sometimes you can eliminate some there. 2, 5, negative 6, negative 15. And I'm going to try 1 again. So 2 times 1 is 2, plus 5, 7. 7 minus 6 is 1, 1, negative 14. So that didn't work. So let's try our next number. Let's try 3. So 2 times 3, 6 would be 11. 33 would be 27. 81. 81 minus 15 is 66. So it's not this one. Now, there is a theorem when you deal with the upper bounds and the lower bounds that might help you. Once all of your signs are positive, that means a greater number is not going to be a root. It's still going to continue to be positive because all you're going to get here then, if you increase this like to 5, then we're just going to get a bigger number here, which will give us bigger, bigger, bigger. So there's no point in our trying those numbers greater than 3, 5 or 15. So, or 15 halves, which would be 7.5. So that helps us eliminate some. Another thing, our rational root theorem says we have 1 gave us negative 14, 3 gave us positive 66. So our answer, our 0, has to lie somewhere between 1 and 3. Well, that means then that the only other choices would be our 3 halves and our 5 halves. So let's try those. So I'm going to try 3 halves, and I've got 2, 5, negative 6, negative 15. And you can go off to the side and multiply 3 halves times 2. Usually, dividing by 2 or multiplying by 1/2 is the same as dividing by 2. So a lot of times that's easier. Half of 2 is 1 times 3 is 3. Half of 8 is 4 times 3 is 12. Half of 6 is 3 times 3 is 9. So that gives us negative 6. So it's not 3 halves. So let's try 5 halves. Okay, half of 2 is 1 times 5 is 5. Half of 10 is 5 times 5 is 25. Now, we can't take half of 19 exactly, and so there's no way that it's going to end up being a positive number, or it's going to end up being positive 15. So that's not going to be a 0. If you wanted to go ahead and finish that part up, it would actually be 95 halves, which combined would give you 65 halves. Which again lets you know, well, it's somewhere between 3 halves, 1.5, and 2.5. We know it's not 1. And, well, so what we know then is it was not a rational root. So evidently that 0 that comes somewhere between 3 halves and 5 halves is irrational. So we need a different way of finding it. So what we're going to do is we're going to go back now and try some of our negative numbers and see if we can find a negative root to reduce our equation. We still use the reduced equation. So we might try negative 1. That would give us 2, negative 2, 3, negative 3, negative 9, 9, negative 6. So it's not going to be negative 1. Well, let's try our negative 3. And you don't have to go in this order. I'm just picking our numbers kind of in order as we go through. Normally I like to do my integers first because they're just a little bit easier. But we have negative 6, negative 1, 3, negative 3, 9, negative 6. Let's go ahead. There's something that when it ends up this negative 1 and negative 3, we got that same answer. And so that tells us some things, but let's just go ahead and try the negative 5. Since that didn't work, negative 5, 2, 5, negative 6, negative 15. That would be negative 10, negative 5, positive 25, so 19, negative 95, which is negative 110. Now, once this last number starts getting very, very big, then most likely your 0 is not going to be a number that's past that. So I've tried my -1, I've tried my -3, -5 started getting a huge answer, getting a lot further away from 0. So I would probably go back and try uh, some of my fractions since those weren't working. So the fractions I have to try are 1/2, 3/2, and 5/2. Well, we could go through and try a couple of these. One of the things, if I took my reduced equation, which I'm finding, it's negative. If I put in a 0, I would get a -15. When I put in -1, I got -6. So most likely it's not between 0 and -1 because I got that same answer. Well, when I go down to -3, I still have -6. Now, I had that same two answers, and what I ended that tells you is somewhere you had to go on down or you had to go up and change directions. But it doesn't mean I crossed the x-axis. So uh, it doesn't really help me as far as my signs go then to know exactly where to try. But I would probably start trying either between these two numbers or between these two. And I'm going to start between these two simply because these were the same. I know I changed directions, but that doesn't mean that I crossed the x-axis. So the number that I have between 3 and 5, what I'm saying is I would try either the -3/2, -3/2, or -5/2, and to see which one I would get. So let's try the -5/2. And so we're using that with 2, 5, -6, and -15. Okay, half of 2 is 1 times -5 is -5. That gives me 0. So this would be 0. Half of 6 is -3 times -5 is +15. So that gives me 0. So 5/2 is also a solution. What I have left is a quadratic. It's going to be 2x squared minus 6 equals 0. So we would add 6, divide by 2, and then take the square root of both sides, which says then that x is equal to plus or minus the square root of 3. So I have my 4 solutions. X equaled plus or minus the square root of 3, x equaled -5/2, and then the other one that gave me a 0 was x equals 1. Now there was one thing that did happen earlier that if you had noticed it, then it might have helped you and you could have done this a little bit faster. The problem is it's not going to happen very often, so I wanted to go ahead and show you, what you would do, how you would just keep trying the numbers. And so it's not something that I would spend a lot of time looking for because most of the time it's not going to happen. But it happened right back here when we found our first 0. And if you looked at what we had left, the 2x cubed, we have 2x cubed plus 5x minus 6x minus 15. So let me just write that down. We had 2x cubed plus 5x squared minus 6x minus 15 equals 0. Well, it just happens we've got a polynomial, but we could factor by grouping. So right here we could factor out an x squared and have 2x plus 5. Here we could factor out a 3 and have 2x plus 5. So we have 2x plus 5 times x squared minus 3 equals 0. So we would have x equals -5/2 and x equals plus or minus the square root of 3. So that did happen. It does not happen often. So that's why I didn't point it out at that time and quit doing the problem, because I wanted you to see all the steps that you normally go through to solve these problems. Let's look at one more, and all of these are fairly long. There's not a shorter way of doing them uh, using our techniques. So let's take this one. We have 4x to the fifth. That means we're going to have 5 solutions, plus 12x to the fourth, minus 41x cubed, minus 99x squared, plus 10x, plus 24 equals 0. Oh, that's a whole bunch. Well, let's look at our possible roots. Factors of 24. And I'm not going to put the plus or it's kind of hard for me to write the plus or minus, but we know that they're there. So we have 1, 2, 3, 4, 6, 8, 10, 12. Whoops, not 10. What am I thinking? 12 and 24. And that's the plus or minus for all of those. That's my factors of the last term. I have to put all of those factors over my factors for my leading coefficient. Well, the factors of 4 are 1, 2, and 4. Well, we've already got all the 1. So then we have to go through and divide them by 2. So we would have 1 divided by 2. 2 divided by 2 is 1. Then 3 divided by 2. 4 divided by 2 is 2. 6 divided by 2 is 3. 8 divided by 2 is 4. 12 divided by 2 is 6. 24 divided by 2 is 12. So we didn't have to do a whole bunch of others when we had our factor of 2. Well, then we also have to divide everything by 4. So 1 divided by 4 is 1/4. 2 divided by 4 reduces to 1/2. 3 divided by 4 would be a 3/4. 4 divided by 4 is 1. 6 divided by 4 reduces to 3/2. 8 divided by 4 is 2. 12 divided by 4 is 3. 24 divided by 4 is 6. So even though both of our numbers had a lot of factors, it didn't really give us a lot to try. Okay, if we look at our signs, positive, okay, we go from positive to negative, negative to positive. So we have either 2 or 0 positive real roots. If we substitute in, and I'm just going to go ahead and change the signs of the ones that are odd powers, so that would be negative 4x to the fifth plus 12x to the fourth. This would then be a plus 41x cubed minus 49x squared minus 10x plus 24. So as far as our sign changes, we have 1, 2, 3. So we have 3 or 1 negative roots. So now we want to start finding them. Well, I would start with the negative because I know I have a negative. I don't know for sure that I have a positive root because I might have 0, but I do know I have a negative root, a negative real root. Now, that doesn't mean it's a rational number, but those would sure be easy ones to try. So I've got 4, 12, negative 41, negative 99. I think I put a 49 here. That's actually a 99. 10 and 24. Well, I would start then with negative 1. So that gives me 4, negative 12, negative 4, eight, negative 8, negative 12. I'm making mistakes here because there's a 41 up there. So that's not 4, that's a negative 41 minus 8. I'm not doing a good job of copying down my problem. So this is negative 49. Hopefully I haven't messed up again. So that would be 49 minus 99 would be negative 50, which would be positive 50, 60, negative 60, which is negative 36. So negative 1 is not a root. Now, once it's not a root for the original one, it won't be a root for the reduced one either. So we can do away with the negative 1 forever. Wait, well, let's try negative 2. So we have 4. So we have negative 8, 4, negative 8, negative 49, positive 98, negative 1, 2, 12, negative 24, 0. So negative 2 is a solution. So that's going to be one of our roots, is the negative 2. And now we have a reduced equation. And not only do we have a reduced equation, but our last number is 12 now instead of 24. So now we can eliminate the 24 and the 8. So let me just write these numbers that we're going to try. It would be 1, 2, 3, 4, 6, and 12. And it would be the plus 1, because we've already eliminated the negative, then plus or minus, plus or minus. Now we would still have the 1/2, the 3/2, the 1/4, and the 3/4. So we still have those to try. Now we found one. We could try to find the positive, or we can try to find another negative. I'm going to go ahead and look for another negative. So I'm going to try negative 3. So we get negative 12, 8, negative 8, 24, negative 25, negative positive 75, 74, negative 222, which is negative 210. Now, we mentioned before, once they start being super negative or super positive, probably they're not going to be going in that direction. So let's go back then and try one of our fractions. So let's try the negative 1/2. And let's see if that even makes any sense. On our problem that we had, and we're using the reduced one, if we plugged in a 0 for x, we would get a positive 12. When we didn't try negative 1 again, did we? So we can't know if at negative 1 we had a, we know that negative 1 didn't work. That's why we didn't try it. So, but we had a 0. So, I don't know. Let's just try negative 1/2. I was trying to see if there was a logical reason to try it other than we're needing to go to some of our smaller numbers, and it was the first one. And I guess that's a good reason. Well, half of 4 is 2, and it would be negative. Half of 2 is 1, it would be negative. Half of 50 is 25, so we get 24. Half of 24 is 12, and it would be negative. So that was a solution. So now we know that negative 1/2. Now, since we found a second negative solution, then that means there is a third one. because it was 3 or 1. We did find a second one, so that lets us know there's a third one. So we now have a reduced equation, and we're going to take that and try to find uh, another solution of it. So let's see where we could go with that. We've got 4. Now, if you wanted to, you could factor out a 2 there because all of those are even. And so we could factor out a 2 or divide it by 2 and go through, and that might make it easier. Or you can stay with the 4 and the 24. And so that part's just kind of up to you. But remember, this is another factor, and we've got our set equal to 0, and so we can factor out a 2 for that factor. So let's do that just to make our numbers smaller. And that means we've got factors of 12 divided by factors of 2. Well, up here we had all of our factors of 12, and we can now eliminate the ones divided by 4. We don't have to deal with those. And we're doing our negative numbers. We already eliminated -1, so we don't have to do that. Now, we didn't go back and try -2 again, so we could do that. Would be -4, -3, 6, -19, 38, which would be 50. So it's not -2. So we're done with -2. -3 did not work up here, so it's not going to work in the reduced one. So we could go from there. I would probably then go with some of my fractions and going again with the -1/2, or the -3/2. So okay, half of 2 is 1. That would be 0. Now we can't take half of 25 exactly. This would be 25 halves. So that would be some positive number. So let's try the -3/2. Half of 2 is 1 times -3 is -3. Half of 2 is 1. This is -1 times -3 is +3. Half of 22 is 11. So this would be 33, and that would end up being 45. So the 3/2 isn't working. Well, then we're going to have to kind of go back with some of our integers. So we tried the 1, -1, it didn't work, -3 didn't work, -2 didn't work, so let's go ahead and try our -4. So that's -8, -7, 28, 3, -12. Well, that's nice. So that works. So -4 is also a solution. And what we have left then is 2x squared minus 7x plus 3 equals 0. We can solve this either using the quadratic formula or factoring. It is factorable, but let's use the quadratic formula. It's the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that would be 7 plus or minus 49 minus 24 over 4, which is 7 plus or minus the square root of 25 over 4, or 7 plus or minus 5 divided by 4. If it's the plus, 7 plus 5 is 12, divided by 4 is 3, 7 minus 5 is 2, divided by 4 is 1/2. So there were 2 positive real roots. We had 3 negative and 2 positive. And all of these were rational, which is not always the thing that happens. But we had -2, -1/2, -4, then +3, and +1/2. But going through and finding your roots, a lot of it's just trial and error, but you want to use those tools to help you narrow down so that you're not trying every number and every sign. And this is how we go about solving our polynomial functions.